For today's video on your review of your exponentials, and I haven't done review videos in the past, but I thought I would do one for this unit, particularly because my voice is not holding out very well. So what I'm going to do is I'm going to walk you through the 6 homework assignment sheets that we've done on exponentials and talk to you about common errors, problems that I saw as I was walking around working with you, difficulties that people were having. We'll kind of put the whole unit, the exponential part of it anyway, together and talk about compare, contrast, things like that. So let's begin with the day 1 video. And the day 1 video was really all about reviewing laws of exponents. There was nothing new in that video. It was all things that you've done before, but students tend to have a lot of problems with working with exponents because they don't keep the rules straight. And it's easy to understand why. There's an awful lot going on. When you just look at the first 4 examples on this page, whoops, sorry, hold on. Okay, the first 4 examples on this page highlight the differences between the rules. In the first one, we're multiplying, and when you multiply, you have to add the exponents. Well, that's different than when you're raising exponents to a power. When you're not multiplying bases here, you're only raising that 5 to the 2nd power, and that's when you multiply your exponents. So again, in one case, I'm going to add the 3 and the 4. Let me show you by contrast when you would multiply the 3 and the 4. So take a look here, we're going to add the 3 and the 4. Here we're going to multiply the 3 and the 4. So when we're down here, we're multiplying the 5 and the 2. That's a division sign right there. If you see a division sign, you can turn it into a fraction. Sometimes it's easier to see things when you turn it into a fraction because the division sign really isn't an algebraic, well, it's a symbol, but it's easier to see for most people like this. That I think most of you would subtract 6 minus 4. And number 4, the important point about number 4 is that you do not multiply the bases. It's very tempting to do that. Take the 10 times 10 and write 100 here, but that's not the case. It's just as though you had x to the 2nd times x to the 4th. If you had that, you wouldn't be coming up with a 2x. You'd just be using the x again in the answer and adding the 2 and 4 and getting 6. As we move across the page, we start throwing parentheses into things. And so those parentheses that we throw in there, we have to be very careful that the exponent only applies to what's in the parentheses. And since they're monomials in all our parentheses, they apply to each piece of that monomial. So you'll take the y3rd and cube it. That'll give you the y to the 9th. You'll take the z and cube it. That'll give you z to the 3rd. You have no reason to do anything with the x squared. You'll take care of that 2 down the bottom. And when it's all said and done, you want to make sure that you have no negative exponents. So the question is, how do we deal with negative exponents? And everybody wants to say flip. Well, flip is true in one case, but that's actually on the next sheet. So I'll hold off on that. Let me just address a few things left that are here. This is a very common regent statement. Express something, a variable, in terms of other variables. When you see that, just solve for y. Whatever, when it says express y, solve for y. If it says express x in terms of p, q, r, s, and t, just solve for x. That's what it means. Don't let that throw you off. On page 2 of that video, really I think page 2 is a little bit easier. Remember, anything raised to the 0 power is 1, but don't raise things to the 0 power that aren't supposed to be raised. If I had this, take a look at the difference between problem 18 and this one. In problem 18, I am actually raising the minus to the 0 power. In this one, I'm not raising the minus to the 0 power. So this piece would become 1, but my answer would be a negative 1 there. Simple substitution, whenever you see f of 3, f of 2, g of 7, that means take that value and put it in place of x in your original equation. And then these were practice in actually simplifying in proper order. If you've shown me substitutions, anytime I ask you to do a substitution like this, that's what I'm asking you to do. Show me the substitutions properly with the parentheses, and then you'd be allowed to pick up your calculator. Okay, we had a lot of rules in this unit about when you're allowed to put a calculator answer and when you're not. Well, these are just simple evaluations. So if you've put in the correct substitutions with using the parentheses like I do, then you're free to pick up the calculator at that point and get an answer. When we moved on to day 2, Oh, hold on, now you've got the sheet with all the negative exponents on it, and negative exponents we take care of by moving. We only move what needs to be moved. We don't need to move anything that doesn't have a negative exponent on it. So if you take a look at any of, say, this problem right here, the only thing that has to be moved in this problem is the a to the minus 3. You're going to leave everything else alone because there are no negative exponents there. And where do you move things? Well, if they start out at the bottom, you move them to the top. If they start at the top, you move them to the bottom. But only move what has a negative exponent. Leave everything else alone. So here we leave the 9 on top. We leave the x squared on top. When you move a to the minus 3 up, there's nothing left on the bottom, and we don't write denominators of 1. The only time we flip, people like to say flip when they see negative exponents. The only time you can flip with a negative exponent is if you actually see, ooh, the pen's moving on its own. If you actually see a fraction inside the parentheses and there's some negative number up here. That's when you can flip that fraction over. Remember, I showed you on day 1 that flipping that fraction is a shortcut for moving. Okay, so really what we'd be doing is we'd be putting a 2 to the minus 7 over 3 to the minus 7, and when we move what we have to move, the 2 comes to the bottom, the 3 comes to the top, and that's another way of writing 3 halves to the positive 7. So we just did a shortcut for moving by flipping that over. So again, don't be too tempted to just flip fractions over. Down the bottom, and remember that your simplified answers do not have negative exponents. This was for instructional purposes only, that we let you leave the exponents, the negative exponents, in this section. But in a normal answer on any test or any Regents exam, you do not want to leave negative exponents in your answer. It won't be a simplified answer unless you have instructions to the contrary, which is rather unlikely. Okay, so that was day 1, taking care of our laws of exponents, including negative exponents. And then we started talking about fractional exponents on day 2. You start seeing all these little fractions, you should be thinking radicals. And you know, a lot of you didn't like it when we got to solving those fractional exponent equations and I was forcing you to show me radicals on your paper even though you could get calculator answers. Well, this is why. Because fractional exponents are radicals. We spent a whole day, a whole sheet, turning all of those fractional exponents into radicals and then coming up with answers. In theory, or in truth, none of the problems on this page, there are no variables on that first page for day 2. So sure, you could have just plugged them all in the calculator and gotten answers. Well, nobody had any issue at that time. So I want you to apply the same thinking when you're solving equations and you find fractional exponents. Turn them into radicals first, then you're free to pick up the calculator. And how do you turn it into radical? Well, when you start with a fractional exponent, you've got an a on top and a b on the bottom. It's really simple to turn into a radical. It takes you all of a couple of seconds. You take the base and the top of the fraction and you put that under the radical, and you put the bottom of the fraction in the pocket, also formally known as the index. If the bottom is a 2, you don't need to write 2's, you can leave them invisible. If it's any other number, you must write it in there. And you can go from there. So that was the first side. On the second side, we were going in reverse direction. Typically, a simplified answer is a radical answer with no fractional exponents. So that's what you should be expecting to do on your test unless you're asked to leave the exponents as fractional exponents. Okay, so simplified means we don't have any fractional exponents, we don't have any negative exponents. And you can see that in this set of instructions here where it said express in simplest form, and that meant get rid of the fractional exponents. You shouldn't worry too much about having to simplify high powers of numbers. It's rare that you're going to be asked to do something like that. If you did see something like that, you would just get all prime factors and you'd be taking out 5 at a time. I don't spend a lot of time doing that because it's unlikely that you'll be asked to do that. But if you are, then just factor down to all prime factors. When you see 5 of any one number, you take it out front once. And then for every time you see 5 numbers, you take them out once. Moving on to day 3, where we started talking about exponential graphs. A couple of important points I'd like to make on these exponential graphs. First of all, notice on the first 2 problems that we had to do, 3 to the x and then 1/3 to the x. Well, we took the reciprocal of that 3. And I just want to show you an alternate way of thinking about this. You can know that when you have reciprocals in your bases, that those two equations will reflect over the y-axis. You can see that in the picture. The 3 represents the growth and the 1/3 represents the decay. You've got a nice reflection over the y-axis. But I want to rewrite these two equations to show you a different way of thinking about this. It'll be more consistent than what we do with our function transformations. Y equals 3 to the x. Well, I am going to write the second one as y equals 3 to the negative x. Remember, we can change a negative exponent by flipping a fraction over. So let's say I started out with 3 over 1 to the minus x. If I flip that fraction over, it leaves me with 1/3 to the x. So these two are equivalent functions. That's the same thing. When you have a negative, and you're doing transformations, when you have a negative in with the x, it becomes a reflection over the y-axis. You've changed every x value from positive to negative, so you see a perfect reflection over the y. The last point I want to make on these exponential graphs is that you do have an asymptote. Use my blue. The asymptote for these is the x-axis. The equation of the x-axis is y equals 0. And you might be asked to find the asymptote for the axis for the equation, because this x-axis, y equals 0, is an asymptote. When you draw the graph, you're going to bring that line all the way down. You don't have to plot all these points, but bring the curve down and let it ride along the x-axis. Put the arrow at the end. Make sure it doesn't go over the x-axis. The fact that you're showing this riding along the x-axis, just get close to it, above it, and make an arrow there. If you have any doubts about the way you drew it, you're a little bit concerned, just make a little note saying x-axis is asymptote, does not cross, and I'll take care of that. Other exponentials, those are pretty much the same. You don't need to spend a whole lot of time coming up with a lot of these kinds of points here. If you look at these numbers, who's going to be able to tell if you actually plotted 0.056 or if you actually plotted 0.054? So I wouldn't spend a lot of time on those. Just write down whatever your calculator gives you. Give me a couple of points down near the x-axis, just 2 or 3 at the beginning, and then just draw that tail out on the rest of the graph. When you're given a grid like this, if you're given a domain, honor the domain. You were given no domain here, so we'll put arrows on the ends of the graph. If you are given a restricted domain, if I asked you to graph only until, and we've got the point 10 here, we have to graph only up to 10 on the x, so I have minus infinity, minus infinity out to 10. Then you would stop that graph at 10. You'd have to put the dot there, and there would be no arrow. So that's just basic graphing. That's true of any time you're making a graph. No arrows on that side. And there's one other point I wanted to make. When you're making these graphs for me, it's up to you to choose an appropriate scale. And choosing an appropriate scale is all about seeing what happens in your calculator before you start drawing on the grid. And that same idea is true when we get to solving exponential equations, because especially with exponential equations, we're usually not talking about a minus 10 to 10. It's a window. We often have numbers that are in the thousands or the hundreds, and it's totally about looking at your calculator first and making decisions about what you should be putting on your paper before you start drawing on the paper. So after you see that if you've got to draw up to 10 here, if the restricted domain said go to 10, you'd have to be accommodating up to 17 on your y-axis. Well, okay, I'll use 20 because then my block counts will work out nicely, and you could take it from there. So having talked about the exponentials already a little bit, let's just move on to that sheet, and I'll show you the applications first. A couple of comments on these. First of all, you have a couple of different kinds of functions that you might be using. You might be using a function that comes from the that original p equals 1. A equals p times 1 plus or minus r raised to the t power. That's where this comes from. But when you're given something like this, that's what you'll use. Don't start messing around with the formula. Just use the one that you've been given. The other type of problem you might get is one that uses the continuous compounding, continuous growth, continuous decay, and those have the E in them. Again, that's a function. If you're given a function like that, use it. Don't be changing it around. I know year after year on tests we'll give people these functions where they have E's in them, and they'll decide to change them to the ones that don't have the E's in them. Please don't do that. Honor whatever you've been given on the paper. Sometimes you have to create your own function. If you have to create your own function, you're going to have to know what those formulas are. So let's go back to page 1 of this video where we have the 3 basic forms. The total amount is equal to the starting amount times 1 plus or minus whatever your rate is raised to whatever your time period is. And you might have seen a second version of this, which I will talk about in just a minute. I only use this version. I don't like to memorize things, you know that. When I use this version, I make sure that the units match on those 2 yellow numbers. If I've been given a rate in years, an annual rate, then I make sure this T is annual. If I have to compound quarterly though, I have to put quarters in my T, and I'll have to divide my annual rate by 4 in order to get a quarterly rate. The alternative to that, which you probably have seen, is that in the formula you see this. It's over N and there's an NT here. And so what that does is it assumes that R is always an annual rate, and you're going to divide that annual rate by 4. And you're going to put the 4 up here to get the number of quarters instead of the number of years. So I would suggest you stick with the red here and just always make sure that whatever units of time your rate is in, that's what you put your time in. And you can make the adjustments from there. So there's that version, and then there's the other version that you have to come up with, and I'm looking for one of those. Go to page 2. Oh, there are none on page 1, so let me show you that one. That's where the final amount is equal to the principal times your constant E with an RT up in the exponent. And again, there's your constant rate. That R right here could be a plus indicating growth, or it could be a negative number indicating decay. So if you have to set up your own equation, you'd be using the red. But if you're given an equation, please use it. Here you're given an equation, you'll use the one that's given. You have to create your own on these 2 with the information from the problem, so just read the problem carefully. And let's talk a little bit more about what you need on your graphs here. For me, I think this is a waste of your time to be writing all those digits, copying it from the calculator when you're trying to finish your test. If you want to do that on the Regents exam, you get bored. It's only an hour and a half and you get nothing else to do. That shouldn't really happen. But yeah, sure, you can start writing those down, but please don't do that on the test. You just don't have the kind of time to do that. It's not necessary. If you put a 300 here and you put a 600 here and you put a 900 here and you put a 1200 here, I'll know what those other numbers are. That's what a scale is all about. Again, you're going to choose an appropriate scale after you found the intersection point on your graph. Then you'll choose an appropriate scale, and do not spend the time identifying every block. We just don't want to do that. So I'm going to take off. Oh, I'm going to take that off. I'm going to take that off. I'm going to take that off. And that leaves me with every other block. You don't even need to identify every other block. You can identify every 3rd block, every 4th block, every 5th block. You know, give me at least 3 numbers. Give me a 0 and give me at least 2 other numbers. Otherwise, I can't tell what your scale is. But I'd say 3 numbers, a 0 and then 3 other numbers, including the maximum, would be fine. You shouldn't really have too much of an issue down here. Most people have the problem here. For some reason, they like to label every number. I know why. It's because when you pick up your calculator, start looking at the table, it starts listing everything in an integer order. So you think you've got to go one at a time, but you certainly don't have to do that. So avoid that. What is important on your graph is that you are showing a graphic solution, and just putting the exponential curve on the graph does not show a solution. The only thing that shows the solution is to figure out what your y value is supposed to be. That's going to be your ending amount. Put that y value on put it on your calculator screen, because otherwise you won't be able to identify that intersection with the precision that you need. When you put it on your calculator screen, when you go to transfer to your graph, make sure you label it y equals, or in this case it's a p sub t equals, and write that number down. Excuse me. And also, because this graph is not nearly so precise that we're going to be able to figure that out, that dot is 5.959. That's kind of silly to think you can do that. Circle that intersection point on your graph and write that x coordinate from your calculator. And that's gotten from your calculator by actually doing intersection. And by the way, graph page, when you're on it, go to menu, go to settings, and make sure it says float. If it doesn't say float and you need to round to thousands, you might not see the thousands decimal place, and there's no other way you're going to get it. So please be sure you're doing that. Change graph settings to float when you're trying to find these intersection points. Make sure you have labels. Please put a word on the x-axis. Oops, I don't mean the highlighter. Put a word on the x-axis. Put a word on the y-axis, and that should work out better for you. We're no longer dealing in x's and y's. Also remember that when you go to plug it into your calculator, you can't plug t's or any other variable into a graphing line. It's got to be x's. And then the last couple of sheets that we did in this unit, solving fractional equations and solving exponential equations. The key when you see equations that you have to solve and they have fractions, the key is to raise to reciprocal powers, but make sure that you have those fractions by themselves. That x to the 1/2 needs to be by itself before you raise to the 1/2 power. And always change those fractional exponents into radicals on your paper before you give me an answer, as you've seen me do in my keys. Moving on to that last page there that we just finished not that long ago, same bases. The biggest problem there is when you see that you don't have same bases, but the numbers can, they're reciprocals of each other. So you can always turn this one into a 6 to the -1 and then work with whatever you have there. Okay, at this point, I'll pass out the review sheets and you get started on the review sheets. If you have questions, feel free to work together as long as you keep it down to a dull roar and you're working. If you do have questions, you can ask me, but I don't know how the voice is going to be, so I might have to whisper an answer at you, so just bring it over.